So I want to talk about some various extensions that we can do with this. And the first one might be, what is the benefit of doing this in general form with, instead of specific numbers, variables? And the idea is that this will really help show us the motivating factors behind why a player would defect or not, and what might influence that, like how they would respond to changes in the payoffs. So I'm going to start by looking at a player playing someone who's playing tit for tat. So I'll have player 2 be a tit for tat player. And we've seen this in the previous examples, that there are two ways you can defect against a tit for tat player. Again, we're always comparing to pure cooperation because we want to see if it's possible to get the cooperation. There's two reasonable alternatives. One is defecting forever, and one is defecting to take advantage of the other player, then cooperating so that it sort of resets their tit for tat strategy, then defecting again, then cooperating, sort of cycling back and forth. And we can write down our payoffs instead of as numbers, as the difference between these. It's actually the same way that we were calculating this stuff before. So if you defect forever, I'll put the rounds down here, but what do you get as a benefit from that defecting forever is H minus C, right? That's the initial benefit, is that you screw over the tit for tat player and you get H, which is greater than what you would get if you cooperate, C. So that's the size. H minus C tells you how much extra gain you get in that first period when you do it. And then after that, remember, you're defecting forever. The other player is responding to what you did in the previous round. It's just going to be D's all the way down to the end. So what are you losing? You're losing the difference between the cooperate payoff and the defect payoff. Notice I'm writing them here actually in positive instead of as a negative. C minus D as the size of the loss, keeping in mind that's the cost. And so we know that defect if the benefit from it is greater than the cost. And so I'm skipping all the steps of writing out C minus D divided by 1 plus R divided plus C minus D divided by 1 plus R squared, etc. We get this as our outcome. I'm going to leave that alone for a second and talk about the other way somebody could defect. And that is if they defect once, then co-op again, and go back and forth. We looked at, in that case, we don't need to look at all the payoffs continually. We just need to look at the one round where they defect and the one round where they sort of take a big loss when they're cooperating again. The gain is the H minus C, but then they lose C minus L, but only for one round, and then they're back to a cooperative point, and they can choose whether they want to defect again. So we know that this one, defect if H minus C is greater than C minus L over 1 plus R. Having these two sort of general forms helps us because it sort of tells us, when are things going to become more or less likely? When will they become more or less likely to defect? For example, if H increases, right, all that does is it increases the benefit side of benefiting for defection, right? Because H is what you get when you take advantage of the other player, when you defect and they cooperate. So holding everything else constant, as H goes up, players are going to be more likely to defect. It's going to make more sense. On the other hand, what if C goes up? Well, if C increases, both of these equations, a similar thing will happen. The benefit side will go down, right? It's a negative, it's being subtracted there. So as it gets larger, that will make that whole side of the fraction smaller. The costs of defection go up. And as C increases, players become less likely to defect, which makes sense. C is the payoff to cooperation. As the payoff to cooperation gets larger, they're going to be less likely to defect. And you can do this with the other payoffs. I think it's worth doing that, and there'll be a problem set question that asks that as well. But sort of keep that in mind, that we can do this, and it helps us see what's motivating them, right? It's really the gap between different payoffs that's the motivating factor here. Another thing that I want to look at is, why am I only looking at the first period? Why am I not looking at what happens if somebody cooperates for 6 periods and then defects? Why might they not? How do I know they wouldn't want to do that? And what I'll show is that the math is just the same, that basically it works out to, if it makes sense to defect ever, it will make sense to defect in the first period. So, for example, if we look at a player playing against somebody who's playing Grim Trigger, we'll use this simple example, and then we say, what do you get if you play Grim Trigger and you defect? Do the same thing, but we'll instead look at what happens if you defect in the third round instead of in the first round. Well, round 1 and round 2, remember, we're comparing to if you cooperate, would have been zeros. Round 3 is the round in which they defect for the first time. They get the +1. And then round 4, they get the -2. Round 5, they get the -2. Right, against the Grim Trigger player, you're going to lose that difference, 4 minus 2, forever. So in terms of payoffs, then, we know that we don't discount the current round. We discount the other rounds successively more and more. The benefit here is 1 over, we need to discount it. If the current round is round 1 and that's in round 3, that means it's 2 periods in the future. It would be discounted twice, right? This is 0. This is 0 over 1 plus r, 1 over 1 plus r squared for that. Is that bigger than -2 over 1 plus r to the third? Oops, sorry, I don't need the -2 on it, right? We're comparing costs. 1 plus r to the fourth, 1 plus r to the fifth, and it goes on indefinitely. Well, these all have a common factor in the denominator of 1 plus r squared. We can multiply this by 1 plus r squared and this by 1 plus r squared. And cancel out our exponents. What do we end up with? We end up with 1 over 2 times 1 plus r plus 2 over 1, sorry, not 2 times 1 plus r, 2 over 1 plus r plus 2 over 1 plus r squared plus 2 over 1 plus r to the third, so on. That's just 1 greater than 2 over r. That's the same exact math we had in the first time. Basically, pushing stuff forward doesn't change the action. When you get to that round, it's the same as if it was just the first round again. The history doesn't matter in this context. It's just when I get to round 3, I will treat it as if it was round 1, and it won't, if it makes sense to do it in round 3, well, round 3 is the current round sometime. So if it makes sense to do it in the current round at any point in time, it will also make sense to do it in the current round right at the start. Finally, the last thing that I want to look at here is this idea of the effective rate of return. The book sort of touches on this and doesn't go super deep with it. The idea here is that there's maybe not total certainty that the game will go on for forever. Players, I mean, in real life, players die, situations happen where you can't be 100% certain things will be infinite. You might have a probability that the game will keep continuing round after round, day after day, month after month, year after year, however, wherever the frequency is. And so this will affect the the way in which we weight future outcomes. For example, in all of these, the benefit comes immediately from defection. So the benefit's quite certain. The costs of defection come in the future. There's already the concern of, I value things in the future less than now, and that's where lowercase r, the true rate of return, comes into play. But then if we add in the probability that the game won't even be played and I will never experience those costs, then it might make me more likely to defect, right? As the probability that the game doesn't continue increases, I'm going to be more likely to defect. We've seen this from when we know that the game ends in a certain round, when we know it's 0% likely to continue, both players have an incentive to defect quite immediately. So I've made up some numbers here, and let's do this again, Grim Trigger style. When you're solving, you don't actually do anything different. Instead of just lowercase r, you just use capital R to keep in mind that there are multiple components of why the future might be discounted relative to the present, both the actual rate of return, but also the probability that the game doesn't continue. So let's see here. Defect versus Grim Trigger in this game. What do you get? Okay, R1 or 2 or 3, blah, blah. In the first round, when you defect, you get a benefit of extra 3. And then after that, you're in the defection world, so you're losing 2. So this is when 3 is greater than, again, skipping all that work. Well, I'll write it down. Fine. 2 over 1 plus r plus 2 over 1 plus r squared plus 2 over 1 plus r third, so on, which we know boils down to that. So this gives me when r is greater than 2/3. Except now, if if I did this regularly, I'd get, as long as if the rate is greater than 66%, the rate of return, then this player will defect. If it's less than 66%, they will not defect. If I'm going to use the effective rate of return with a probability that the game might end, it's fine. This is just now capital R. Nothing's changed about how I solve this, but now I have if the effective rate of return is greater than 2/3. Well, what does that mean? So if you look in the book, you'll see sort of the following. You'll see 1 over 1 plus r equals p delta, right? But delta, so I'm looking at page 386 here, just for your reference, right? But delta equals 1 over 1 plus r, that's page 385. So 1 over 1 plus r equals p times 1 over plus lowercase r. And I'm sorry to say that I'm not going to have like a nice, fancy, fun situation for you with this. What we're going to get is going to be something that will depend on, do I have a probability or do I have a true rate of return? Remember that R is the actual true rate of return. P is the probability that the game continues. I might have one of those or the other. So for example, let me solve for capital R here. That's going to require getting a common denominator for both of these. So I'm going to multiply this side by 1 plus lowercase r over 1 plus lowercase r. This side by 1 plus capital R over 1 plus capital R. So what does that give me? Right, I've multiplied both sides by 1, so that's totally allowed, and then works out to be like that. Well, that means they both have the same denominator now, so I can just cancel that out. And I have 1 plus lowercase r equals p, the probability that the game continues, times 1 plus capital R. Okay. 1 plus lowercase r equals p plus pr. And if I want to solve for r and get r by itself, right, I'm going to take this up here. 1 plus r minus p equals pr. I've just moved the lone p to the other side. Okay, r equals 1 plus r minus p divided by p, dividing both sides by p, and then flipping them just to rewrite it like this. That's, again, this is not incredibly clear and easy to sort of see, but let's take this and come back over to our solution for this. So if we have 1 plus r minus p over p greater than 2/3. This is only useful if we have a specific, maybe true real rate of return, or a specific true probability the game will continue. So as an example, let's posit, let's say, what if the true real rate of return were, so I'm going to erase some stuff to give myself a little bit more room. What if r equals 10%? That's a very reasonable actual real rate of return. Right? It's not as weird as some of the 100%, 200% things we've been looking at. Like for an annual rate of return, that seems very reasonable. Well, what if r equals 10%? Plug it in, we would get this player will defect if 1 plus 0.1 . Okay, so we're still not totally there. We have to solve for p, right? This is 1.1 minus p over p greater than 2/3. So let's move the p around, multiply both sides by p. 1.1 minus p greater than 2p over 3. Multiply both sides by 3. Okay. Then add 3p to both sides, right? So I'm going to take this up here. Divide by 5. What that says is this player will defect in this game if the real, with these payoffs, these specific payoffs, right? This is not general, these are these specific payoffs. And with a true real rate of return of 10%, if they think the probability that the game will continue is less than 3.3 over 5, which is 66, if they think the probability that the game will continue is less than 66%. So this is a relatively reasonable, but low relative to numbers we've seen, actual rate of return, actual lowercase r. And so what this says is like, this is a relatively low rate of return. If they're very sure that the game will continue, then they're going to cooperate, right? This is all set up as when would they defect, right? Remember we set up our paths as like when will they defect. So you think about they will defect in this case with this rate of return only if they're relatively confident that the game is not going to continue, or I guess moderately confident. They think the probability of the game will continue is less than 66%. And what I would suggest doing here is playing around with this and changing the r, or putting in a p and changing the p, and seeing how these things affect each other. Like for example, what happens if we make r 50%? Let's do that. I'm going to erase a bunch of this stuff over here. This will be the last thing we do with this for now. Get rid of a bunch of this junk so we can compare. What if, oops, not capital R, lowercase r. Well, then we would have, just recopying this stuff, we would have had 1 plus 0.5 minus p over p is greater than 2/3. 1.5 minus p over p is greater than 2/3. Right, so I'm doing the math very quickly. Come back and check. Right, so that last step is multiplied both sides by 3. 4.5 greater than 5p. 0.9 greater than p. So as we increase the real interest rate, that makes people less patient, right? Now they can, even if they're relatively confident the game will continue, even if they're 80% sure, it's not worth cooperating. They will defect because the real rate of return is so high. If the real rate of return is 50%, right? As the rate of return drops, like if it gets very, very low, that means, right? So the rate of return you should always think about as being a measure of how much things in the present are valued relative to things in the future. Higher rates of return mean that the present is much more valuable than the future. So as the rate of return increases, the present is becoming much more valuable in the future. Even if players are very confident the future will happen, it doesn't matter. It doesn't have as much weight. If we flip and go the other way, as the rate of return decreases, that makes the future more important. It gives the future more weight. So in order to defect, a player has to be more confident that they will not suffer, they will not have to play the game and suffer those consequences in the next round or the round after that. This is a little bit difficult. I think it's worth playing around with and thinking about. There will be probably a problem set question on it. And we can talk about it in class or in office hours as well. But try playing around with it and try some of the examples in the book. All right. And that's all I got.